Hi, I'm Adithya, and along with my project partner Kaishavi, we'll be demonstrating our Lab-2 and Lab-3 for the course E542, that is, doing network measurements of a client server testbed on Amazon Web Services. Right. So I'll be covering AWS setup and basically taking measurements for bandwidth, throughput, and delay. And Keshi will be covering how to take bandwidth delay and loss, and she'll be covering the secure copy program that's part of our assignment as well, right? So for AWS, we need a virtual private cloud and we need instances. So instances are basically a virtual computing environments, which will be creating inside our VPC. And basically we can assign, uh, basically we can configure machine images as a template for our EC2 instance. You can basically relate this to a particular virtual machine, right? So the steps are, first we create a virtual private cloud within the AWS and attach an internet gateway to that VPC. So this ensures that all the environments and resources within the VPC have access to the internet. Within the VPC, we create 4 subnets. Why we create 4 subnets? I'll be discussing that in more detail. We'll be needing 3 instances, one as client. So PC1 will be acting as a client, PC2 as a server, and router, which is running YOS. So YOS is an open source IP router, and PC1 and PC2 will be running Ubuntu instances, right? So each instance will have 2 interfaces. So AWS only allows 2 interfaces per instance. And while doing the setup for the instance, we'll make sure that it allows TCP, ICMP, and UDP protocols through the firewall. We have to make sure that we save the key pair to remotely access the EC2 instances. And how we are going to access the instances? Using something called elastic IP addresses. So with the elastic IP addresses assigned to a particular interface on an instance, we make sure that we access that instance using the key pair. Now, there's one thing that you have to keep in mind, that we have to assign elastic IP address to a net interface, which we will not be using in a network topology. Why is that? Because if you do any configuration changes to an interface which has an elastic IP address assigned to it, you won't be able to remotely access that machine. So that's why we need 4 subnets. So we have 4 subnets here within this VPC, which is within, again, the AWS region: 1.0, 2.0, 3.0, and 4.0. 2 interfaces per instance, PC1 and PC2. These are the IP addresses that is assigned by AWS based on our subnet. And now coming back to the elastic IP discussion, we assign elastic IP addresses to each 0 for PC1, each 0 for router, and each 0 for PC2. And our internal network will be created via the ETH1 PC1, ETH0, ETH1, and ETH1 of PC2. So this is our internal network, and we need these links to basically remotely access our instances. Right. Now, I already have the machines running, and as you can see, the YOS, the router instance has these particular IP addresses, private IP addresses assigned by Amazon, and the elastic IP addresses is here, as you can see, and same for PC1. So this is in our ETH0 interface, this is an ETH1 interface, elastic IP address assigned, and same for PC2. Right. So just to show you how we access our machines. So right now you can see that I'm currently inside my server machine. So this is my client, this is my router, and this is my server. So just to show how we access the machine, I'll be exiting out of my instance, and this is the command that we use. So we use SSH using the key pair that we downloaded during the instance creation step, and we use Ubuntu because we are running Ubuntu on this machine. So that's the username for the machine by default. And this is the elastic IP address that is needed to remotely access our machine. So when we do that, we are able to access our machine. So I'll be turning myself into a root user because we'll be doing a lot of configuration changes. So if you can see on the client side, I've written some commands here. So just to show that by default, uh, the secondary interfaces, that is ETH1 interface of the instances, are not defined by AWS. So we have to manually define our ETH1 interfaces in all the three machine instances. Right. So this is the process that we do. So this is the private IP address that is assigned by Amazon. This is my net mask for this particular address. And we need to basically add the routes to create our network topology within the AWS, right? So we are trying to send packets of whatever. We are trying to basically communicate from client to server. So client is in our 1.0 subnet and server is in our 2.0 subnet. So we want to basically add a route to this particular network via this gateway. So this gateway is basically nothing but ETH0 interface of this router. This way we make sure that whatever packets that we send to the server, it is via this router, right? And dev eth1 basically signifies that whenever I'm trying to communicate to this network, it's done via the eth1 interface, which has this IP address, right? So I've already have this setup in place. That's why it says file exists. So just to make sure that I'm able to listen the packets, I'll be running TCP dump command on my server and router. TCP dump minus I. Oops, any. So this signifies that I'm listening from all the interfaces, even though essentially we're just listening for the incoming ping packets that we are going to do right now. SAMP, right? Enter, enter, and then 0.2.199 is the private IP address assigned by Amazon for my server. So just to make sure that's the case, so this is the address, right? So when I do ping, as you can see, I'm able to send packets and I'm getting the echo request and echo reply of these ICMP. So this way we can come to a conclusion that yes, the connection has been made and it's performing as we wanted to perform, right? So we have the instance setup, we have the network setup. Now the first step that we have to do is to how to do network measurements, how to basically measure bandwidth, how to measure throughput, how to measure delay, right? So there's a command called iperf, which you basically use a tool. It's a command that is basically used to do network measurements over a particular link, right? So we want this PC2 to act as a server and PC1 to act as a client, right? So just be using iperf minus s. This will make sure that I'm using the basically this is acting as a server, right? And just to make sure, by default the interval is 10 seconds. So every 2 seconds it will display the readings. So as you can see, and if I'm not explicitly mentioning what do you call UDP, by default it's TCP. So I do the same here. So minus C signifies client. Where am I communicating to? The server. And same way, I'm just want every 2 seconds the results for that to be displayed on my screen, right? So as you can see, we can see the results for every 2 seconds. So right now, our link is basically transmitting 733 megabytes. So the norm is we calculate throughput using TCP and we calculate bandwidth, the link bandwidth using UDP. So right now I'm using TCP, so you can see that this is my throughput with the current this thing. And just to check what our delay is, RTT is, by default, as you can see, we can run the ping command and you can see it's around 1 millisecond. So RTT average, it's around 0.96, which is close to 1, right? So we see that we get throughput using the TCP, and even though we see the bandwidth, the norm is to basically calculate the link bandwidth using UDP. Why is that? I'll let you know. So clearing the screen, we do the same thing. So we add an additional tag minus U, which basically signifies that it's going to act as a server via using the UDP. And we do the same here. See 10.0.2.199 and basically, and then we signify minus U minus I2 because we are listening to D2 and we need to specify a bandwidth. So let's start with 100 megabits per second, right? We'll see whether we are having any telegram loss or not. Oops, I just realized that I didn't start it here, so I might have to start again. Yeah, so now my server is running. Sorry about that. And when I do that, as you can see, on a when I'm setting 100 megabits per second, I'm getting no loss, right? So we have to do a couple of hit and trial methodologies to make sure that this is the link bandwidth that we are getting. So personally, what I do is if I get a consecutive double zeros, double 0% loss, I keep that as a benchmark and I'll make sure that the bandwidth is always above this particular limit. So right now, the current state of my link has a bandwidth as 100 megabits per second, right? So let's try to increase that. Let's jump to 150. Let's see whether we are having loss or not. Yeah, so as you can see here, I am losing some datagrams in the process. So this signifies that with this bandwidth set for my net link, I am having loss. So our bandwidth should be around 100 to 115 megabits per second. So this way you basically fine tune what your link bandwidth is. So it's a lot of hit and trial working in place. Let's set Control V. So right now we are running with a 1 millisecond delay that is by default, right? So the first task in our hand is to basically do these measurements with different delays. So how to add delay? So we use a queuing discipline for traffic control, which basically adds a delay on the E0 interface of router, right? And a delay. So let's say we start with 100 millisecond, right? So how do we make sure? So first, via router, we see that the E0 interface has this particular configuration, this particular traffic control configuration, right? So just to make sure that it is in fact the delay has been injected, we do a ping command, and as you can see, we are getting RTT of around 100 milliseconds. So that's what we intended, right? So in this way, we basically inject delay in the network, and we'll do the same thing. We'll run the TCP first um, to get our throughput, and UDP to get our bandwidth, right? As you can see here, that the throughput earlier we were getting at the order of some 700 megabytes as throughput. Now we're getting only 70 with the delay as 100 milliseconds. So it has dropped significantly due to the reason that we are injecting delay, which leads to congestion, right? So this is the throughput with this particular delay, and we do the same thing for UDP. Right. I make sure that I'm using UDP, and for UDP you need a U tag, and I'm setting. Earlier we saw that with the 100 megabits per second, we didn't have any loss. Let's see what happens now. Yeah, so as you can see, oh yeah, there you go. We get a loss at 100 megabits per second. So earlier we made a benchmark that bandwidth is going to be above 100 and below 150, or in the order of that, the state of our current link. But now, due to the injected 100 millisecond delay, we are having datagram loss with this particular bandwidth set, right? So we need to basically decrease our bandwidth and basically run it again to make sure that we don't have any packet loss with this particular bandwidth set, right? So now you can see that with the injected delay, our bandwidth, so we can start with a benchmark of 80 megabits per second. So our full link bandwidth should be in between 80 and 100. So as compared to in the previous case where our delay was 1 millisecond, we had 100 and 150. So as you can see that the bandwidth has decreased with the increase in delay, right? So our task was to do these experiments for different delays and to take measurements, right? So now you can see that this is the plotted. So if you see the first half, this basically is our default queuing discipline with just the indicted delay. So we calculated at the time of measurement, we were getting some 58 megabits per second as bandwidth and throughput, and our RTT was reflecting whatever emulated delay was, and we basically tabulated each and every bandwidth and throughput using the iperf command. Now, the second task was to basically use a token bucket filter along with the delay, right? So to use that, we first have to delete whatever we had set. Del dev eth0 root. So if you do a show, we'll go back to default. So this is the default P54 fast that I mentioned here. So this is the default Linux queuing discipline, right? So to have two queuing disciplines on one interface and to basically have token bucket filter along with the delay, we basically have to use this command qdisk add dev eth0 root handle 1 netm. So let's stick with delay 100 milliseconds for now. And now we add a token bucket filter and we assign a speed for the link along with the latency and burst. So the latency here signifies the the time till which the packets will be in the buffer. So after 1 millisecond, the packets will be dropped if it's not sent across. So that's what latency here. So it's not. So the latency mentioned here, which I'll be. Oh, I haven't mentioned it right now. So if I write 10 bit latency 1 millisecond burst. So let's stick with 90155. So this latency corresponds to how long my packets will stay in my send buffer or receive buffer. So that's what it is. Oops, instead of eth0, I write eth0. Sorry for that. So if we do a tcq disk show, we see that the eth0 interface has network delay as well as the speed also set. So our default speed is 10 megabits per second, right? That's our rate. Now to make sure that our link speed is constant, so right now we have done only for eth0, so this corresponds to the client to router link. Now we want to make sure that the speed is constant across the client server link, right? So we have to add this speed in our eth1 interface as well. So for that, since we don't have a delay command for our eth1 interface, we just do a eth1 root tbf rate same as before, latency as 1 millisecond, burst same as before. So if we do tcq disk show again, we see that the eth1 has this, eth2 same as eth1, and sorry, eth0, eth1 has this, eth0s have the delay as well as the tbf, which is similar to the eth1, right? Now we do the same thing again. We calculate delay, we calculate bandwidth, and we calculate throughput. For RTT, we use ping. Remember, we injected 100 millisecond delay, and that's what you're supposed to expect. So we get a 100 millisecond as our delay. Right, now we run uh, TCP first. Let's run TCP. So for TCP, we don't need -u or -b tag, and we'll see with the 100 millisecond latency and 10 megabits per second as our speed for the link, how much throughput are we getting? So as you can see, we are getting some 12.9 megabytes for 10 megabit speed link and 100 millisecond delay, right? So this is the throughput that we are getting. So for bandwidth, we do the same thing. We run it UDP, right? Let's start with 80. We remember we had a 80 megabits per second as our lossless bandwidth setting. So it's, oh, as you can see, now we are getting tons of losses with 80 megabits per second. So clearly it's much less than what we expected, right? So I'm just jumping to 10 megabits per second now. Yeah, right now you can see that I'm not having any loss, some loss. So it's somewhere below 10, and let's check for even less. Let's check for 9. As you can see, I'm not having any loss for 9 megabits per second. So our bandwidth should be above 9 and below 10. That's our link bandwidth with the speed set as 10 megabits and 10 megabits per second, and the latency set as, sorry, the delay set as 100 milliseconds, right? So this way we test for different speeds and different delays. So we basically tabulated our results. So our first column signifies different delays, and the second table within this red block signifies our token bucket filter with the burst latency on the router for 10 megabits per second network speed, 100, and a gigabit speed link, right? So we see that we tabulate all the bandwidth, throughput, RTT, everything within this. So our second step for this particular measurements task was to set a higher send and receive window size. So to see what our current window size is, we first run a command called um, cat proc sys net core am underscore max. So right now this corresponds to 208 kilobytes, and we do for this as well. You see that this is the case, right? So we just copy and do the same to check what my server window size is. So this is my sender and this is my receiver, right? So you have to see what our window sizes is for both of these instances. It's the same here because we are essentially using the same operating system, right? So it's set by the operating system. We're using Ubuntu, right? So to basically see any variation with the TCP window size, with the throughput, we try to, we then take cases for a higher window, right? net.core.rmem underscore max. We set it as 2 megabytes. So for 2 megabytes, it corresponds to 52. So this is our command for uh, setting the max window size. Right? We do the same on the client side as well as on the server side. RMEM, WMEM, right? And then we do the same thing again, which is what? Do ping once again just to check whether we are getting different delay. No, it's going to be the same delay because we have injected the delay manually, right? Now we do throughput calculation. For throughput, if you remember, we did this. If you remember, we did this on the client side, server side, and you can see the variation here. So we calculate throughput as well as the bandwidth using the same methodology. Now we have a higher window size, right? Now this is the throughput that we're getting. For bandwidth, we use iperf in UDP mode. So let's start with 9. That's what we had, right, as our bare minimum. So as you can see, we're not having any loss. So bandwidth is again unaffected. So it should be somewhere above 9, and I'm guessing less than 10, the same as before, right? So we tabulate the same set of setup. First, we did it for a default window size. Now we set as 2 megabytes as send and receive window size, and we do the same set of result of measurements. And as you can see, for different network delays, we get a slightly higher throughput, which makes sense because theoretically, if you increase a window size in TCP, you will get a higher throughput, right? And that concludes my part of the demonstration. Now, Casey will take it on from here and she'll be explaining about bandwidth delay and loss along with the secure copy feature. Thank you.
Now we will see the effect of TCP window size and packet loss on bandwidth and throughput. We will insert 25 milliseconds of delay on client-side interface of router. Now we will ping server from client. We can see here that we are getting 26 milliseconds of delay. Hold. Now we will find the bandwidth and throughput of the system. We can see that we are getting 169 megabytes of throughput. Now we will find the bandwidth. We'll use UDP to find bandwidth and TCP to find throughput. Let's estimate the bandwidth. We are still getting less loss, so we'll decrease it more. Here we can see we have got 0% loss 2 times, so we can consider 70 megabits per second our bandwidth. it all depends on link at that time. Since we are doing it on AWS, it varies time by time. So we got the bandwidth. We can get bandwidth delay product by this calculation. We already found the throughput, that is using TCP, that is 169 megabytes. Now the question is, if you left the send receive windows at their default values, would this link perform well? So our observation says that we get lower throughput as we decrease our default window size. So the higher performance will be there if we keep it default window size. Can we scale the sand receive windows to see the effect of a bandwidth delay product TCP window size mismatch? Does it make sense to do so? Here, as we observe that the delay bandwidth delay product dictates how big our TCP window size should be, so we can utilize the link fully. So if TCP window size is greater or equal to bandwidth delay product, we can utilize the whole pipe fully and we can get more throughput. If window size mismatches, if the sender and receiver window size are different, then they'll negotiate upon the window size and choose the list of them. So now I have set the window size too small from the default value and I'll measure the throughput. So here I'll keep the window size as 159 kilobytes. I have to put the half of that value in my command because in Linux operating system it takes its double value. So here at 159 kilobytes we are getting only 49.4 megabytes throughput. So it is much less than around 150 megabytes which we got before. Now, what happens if we have a gigabyte speed link with 1 millisecond of delay? So, with a 1 GB DSL connection, knowing you can only control the receive window size, what will happen? So, as I said, bandwidth delay product dictates how big the receive window size needs to be, so we can utilize the whole link. Here, if we have 1 gigabytes of link, then definitely bandwidth delay product will be high. So we can set the TCP window size much bigger and the throughput will improve. So if we if we can only control the receiver window size, then if the sender window size is less than the receiver window size, then they have to negotiate upon the window size and they'll decide the list of them. So we cannot get high throughput if the receiver if sender window size is less than the receiver window size. Now we will insert loss of 0.1% on the link and we'll observe that that loss can be seen on UDP bandwidth and loss. Now we will see loss using UDP. Since it is UDP, it differs every time. So still we can see that we are getting lost sometimes. Now we will move on to secure copy. The secure copy program SCP is a standard tool on modern Unix-like machines. It is used to copy files between machines securely and reliably. So here first I'll set the network speed to 100 Mbps using TC. I'll also need to default my delay to 100 milliseconds. Now we'll calculate the RTT using ping. We can see it is around 1 millisecond. Now we'll calculate the bandwidth and throughput. The throughput is around 115 megabytes. Now let's calculate bandwidth using UDP. We need 0% packet loss to get our perfect bandwidth. Here we can see we have got almost 0% loss in 50 megabytes megabits per second bandwidth. So here we can calculate bandwidth developed order. Now we'll create and mount a temporary local file system on client. So these are the commands. I have already mounted it on client. Now let's see what these commands do. DD means data duplicator. It duplicates data from output to input. Here BS is the set of block size. If it is 1 M means 1 MB block size, and count it is a number of copies we need to transfer or copy. So the count is the block number of blocks which we need to copy from output data to input. So we can use DD in a network context to send data streams across our lane. MKFS, it is used to build a Linux file system on a device, usually a hard disk partition. It is either the device name or a regular file that shall contain the file system. Chmod, it is used to change the read, write, or execute permission of file or directory. The mount command used to mount the file system found on a device to a big tree structure. I've already created file, and now I've created private key file on client side. So I'll transfer that file to server and we'll see what is the throughput. Here we can see it is transferring the file. The file size is 200 MB and we are getting 11.1 Mbps speed throughput. Earlier we got 11.8. Now we'll put some delay on the link and we'll see what is the throughput. For now the delay is 0 millisecond. Now we'll put the delay of 10 millisecond on the router. Now we'll see the difference of throughput. Here we can see variation of throughput due to the AWS. The link is a little bit unstable and we can get different throughput. We'll analyze for a long series of delays. Now I set delay to 30 milliseconds. We can see the throughput has decreased. Let's change it to 50 milliseconds. We can see the throughput is decreased again. It is now 8 Mbps, so we can conclude that throughput decreases as RTT increase because throughput is equal to data upon RTT. Now we will see if we can change our performance by changing maximum TCP window size. Let's change maximum window size on both sides. Before that, we'll set our delay again to 0. We need to change it both server and client side. We'll again see throughput. We can see the throughput is unchanged. We'll try for different value, much bigger value of window. We'll again transfer the file and see the We can observe that the throughput is unchanged, so we can conclude that we can't improve our performance by changing the maximum window size. Now it is the question, does SCP seem to have some sort of built-in limitation? So here, while SCP works fine in a local environment, it performs poorly on a WAN where there is a need to transfer large data sets along a network path with RTT of more than 20 milliseconds. So it is a built-in 1 MB buffer that severely limits performance on a WAN. SCP typically uses SSH as transport and therefore it is subject to the limitation imposed by the underlying SSH implementation. Now set the delay to 0 and will observe the performance when there are packet loss from 0.1% to 32%. So then I'll explain the graph. We are not seeing any change, a wide change in throughput at 0.1% loss. So increase the loss. Let's see if it changes the throughput. Throughput is still the same. Now we'll set the loss to 5%. We can see the throughput is almost the same. Let's keep the loss to 11%. And see the difference of throughput. We can see the throughput is decreased to 10.5. So we can conclude that after 10% loss, we can see the decrement in throughput. Let's keep it loss 14% and see what happens. We can see decrement in the throughput is now 9.1. Now let's take a 30% loss. I've taken different values and plotted a graph, and you can see it in presentation. You can see the throughput is very less now, almost approximately half. It is 4.4, which is less than half of what we got before. So we can see that here is a graph of throughput versus loss in percentage. So till 1 second, till 10% of the loss, we get the straight line, means the throughput is almost constant, then it is decreasing exponentially. Now, here is a question. Estimate the delay and loss from Los Angeles to Switzerland. If you had a like physicist for a colleague and he wanted to download some data from the new atoms measure at CERN, would you expect him to come to you for help? Can you help him? So here I have pinged a data center at CERN in Switzerland and I got 211 millisecond delay. So it is much higher, but there is 0% loss. So we can definitely help him, but the if he's okay with the this much delay, then he can download files from that data center, but it will take a lot of time. So here I conclude the lab 3 of E542. We have completed that successfully and got the result as expected. Thank you.